Okay, so the second talk is about an evaluation study, which actually my postdoc, PhD, and Sean, a colleague from Curtin University, have done. So in many application areas, linking is difficult because of privacy concerns. So in the health domain, for example. So there has been quite a bit of research in developing what's called privacy-preserving record linkage techniques, but there hasn't been many real evaluation. And what we did here is we compared a production linkage system, which is running at the Centre for Population Health Research in Curtin, Western Australia, in Perth, together with our prototype software, which we've developed over the last few years. So basically, we all know that, in the big data area, companies and governments want to integrate data from different sources to improve decision making. For privacy and confidentiality are a big concern if the data is about people, and it's maybe sensitive information about their finances, their health, and so on. So the objective of what we call multi-party privacy-preserving record linkage is to perform linkage across multiple databases held by different organizations using not the actual values of the records, but we somehow encode or mask them. So we convert them into something which doesn't allow us to re-identify a value, such that at the end of that process, we're only going to reveal information from a small subset of attributes about the records which were linked. So in the health domain, for example, if you link two health databases, we find all the people who have a certain disease, and at the end, we're not going to reveal their names and the addresses, but maybe their age bracket, their gender, maybe the postcode they live in, but not the actual details. But we do need the names and addresses to perform the linkage. So here's an example. Let's assume, and sorry, you've seen this at the introduction workshop, I think. So let's assume a demographer who wants to investigate mortgage stress, how mortgage stress is affecting people's mental and physical health. So you want to buy a house, you get a mortgage, the mortgage goes up, but your salary doesn't go up. So it's a pretty common thing in the Western world. That demographer should need data from financial institutions, from the government, so information about social security of people, the health of people, what education of people, education level, how many children the person has, and so on, as well as private providers such as health insurances. It's very unlikely that a researcher gets access to all these databases for different reasons, commercial reasons, legal reasons, and so on. But at the end of the day, she only needs a few attributes, such as the education level, the financial status of a family or so, but not the actual names and addresses. So we want to be able to allow to facilitate such a linkage, which currently is potentially not possible because of privacy concerns. So privacy-preserving record linkage has been worked on for the last 15, 20 years almost. It's a lot of different techniques have been developed, but most work has only looked at linking two databases. But as we see in the example before, many applications require many databases. Same with the health domain. We might want to find patients who have been admitted to several hospitals across the country. In crime and fraud detection, we want to get information from many different banks. National security, data will come from travel agents, from immigration, from all kinds of sources. So as you have more parties, the computational efforts increase, potentially exponential. We also have the issue of collusion. So basically where a subgroup of parties might work together to try to identify information about sensitive information about a third party. We somehow need to calculate similarities across sets of records. And very challenging is what we're working on at the moment is how do we find matching records across a subset of parties? Let's say we have a group of 10 hospitals, and we want to find all the patients which have records in 5 of any of these 10 hospitals. So how does the whole process work? So again, similar to the record linkage process, we have databases. The first step is that we process them and we mask them, so we convert them into codes so that they kind of can be given to a different organization, so that the mask database don't contain any identifying information. We do some blocking in a private way so that no information can be learned about the source databases. We do some comparisons on these encodings. We do classification, and then we classify record pairs or sets into matches, so the ones which correspond to, we think correspond to the same person, no matches and potential matches. And normally in non-privacy preserving record linkage, we have a clerical review, but I have a question mark here. We don't really know how to do this because we're only working on codes. And then we want to evaluate how good our linkage is. And we're basically now looking at some of the aspects of these three steps. So masking, there's been a lot of different masking techniques developed over the last 15, 20 years. In all the techniques which we evaluate in this study, we're looking at Bloom filters. So a Bloom filter is basically a bit array, so it's a list where one means an element has been hashed, kind of put into that element, in that vector element. And the way it works is we split our values of Peter and Pete into small qgrams or substrings, and then we hash them using a specific function, or actually more than one function, into these arrays. And then we count how many positions. So each time a qgram is put into a Bloom filter, we set the corresponding element to 1. And then we basically count how many positions have a 1 in common. And that gives us a set similarity. So we can basically calculate that the similarity between Peter and Pete here is 0.83. And that has been used quite extensively the last 15 years, the last almost 10 years or so. Very successful with 20, 30 papers working using this technique.
I'm completely lost. What are you masking? What are you doing?
I'm masking my names and addresses into Bloom filters. And the Bloom filters are what I then send to a linkage unit, and the linkage is based on the Bloom filters.
Are you about to release the mask name? What is the What is the setup here?
Okay, I have Peter and I have Pete. So my record 1 has Peter, my record 2 has Pete. I want to find how similar they are. I will do the same for last name, for...
what is the masking here? So maybe you have 2 versions of your name, but what is
the masking? Okay, the mask or the encoding, it's a different word. Okay, sorry, use the word masking different what you use it in statistics, okay? Most probably, again, translation problem. So it's an encoding, right? We encode a string into a Bloom filter. That's less confusing.
So what you're saying is that if a name is written in 2 different ways, you measure the distance between these 2 things.
That's right.
For the purpose of linkage.
Yes, but I'm not, because I cannot send my names away because they're sensitive, potentially. The databases are sensitive. I need to be able to calculate my similarity based on an encoded version, and I'm using Bloom filters to do that. Does that make sense?
This is a code. People don't know this code?
No, it is, okay. There's lots of details how we do these things here. This is the basic overarching idea. So I can generate these Bloom filters in such a way that if you have a Bloom filter like this, if I give that to you, you cannot identify what the string is behind the Bloom filter. Okay?
So you give the researcher a representation, 2 representations of the names, and the researcher will match them?
Not the researcher, no. A linkage unit matches them.
So you don't want the guy who matches them to know the real names?
Right. That's right.
So there's a secret key, and
there's a lot of things involved around that, yeah. Which, because this is a short talk at the conference, I cannot go through. Yeah. And yeah, so have a chat.
But my comment about your lecture is that at least I did not understand what the purpose is. Who are you? Who is doing the linkage?
Okay.
Who is hiding anything from whom?
Yeah. Okay. Right, so we have now our masked records in Bloom filters. The blocking, again, I'm not going to go into the details because there's no time in the presentation. Blocking basically, again, we want to prevent that we have to compare every record in one database with all the records in the other database. So we block the databases in such a way that the blocks don't reveal any information about the actual values.
By the way, why do you mask the way you described only the names? You can mask the whole data.
I do. Sorry, I do that, but this is an example, okay?
I see.
I know you're a different audience than the conference. The conference audience knows potentially more about this. It's a whole session about privacy preserving. So I apologize about this, right? That's so yeah. And again, there's not much details about how we actually do the blocking. So the basic ideas are that's getting more complicated. These three techniques, they take these Bloom filters and they do some clustering on these Bloom filters. Basically try to find similar Bloom filters and they become the blocks. That's the basic idea. And I don't have time to go into the details. One is using a split and merge kind of iterative approach, and the other one is using a hierarchical clustering approach. The third step then is to now take the Bloom filters in the same block and to basically compare them, and then to classify them into, they have a high similarity to matches, if they have low similarity to non-matches. Again, the challenge here is we can easily do this on two databases, but as the number of databases goes up, it becomes much more complicated with regard, because we now have sets of 3 or 4 or 5 such Bloom filters. And unfortunately, the machine which was used at the linkage center in Curtin didn't have that much memory. So all our prototypes, which are not optimized, 2 out of 3 prototypes didn't work on that machine. So the one which we evaluated is a graph-based clustering approach. So basically we take 2 databases, we compare the Bloom filters, and we cluster similar Bloom filters which correspond to the same person, we assume, into small clusters, and then we link these clusters to the Bloom filters from the 3rd database. We build new clusters and we link them to the 4th database and so on. And that has a quadratic complexity in the size of the databases. If you zoom in, it's the number of records. And it's independent of P, the number of parties. While earlier work by my postdoc, the complexity involves P, the number of parties, right? So N over P, that doesn't scale with the number of parties. Okay, so how did we actually do the evaluation? Again, the evaluation is the main aspect of this work. So we had a set of data sets, 3 and 5, emergency presentation data, that is real health data from New South Wales in Australia, and they were linked in New South Wales by the Centre for Health Record Linkage. So that's kind of our ground truth. So that's a normal linkage process with lots of clerical review by experts, and shown the person who did the linkage at Curtin University, he had access to that ground truth and to the data set. So these were our data sets which we now tried to link in a non-privacy preserving way and in a privacy preserving way. So we basically used blocking attributes and linkage attributes in the same way as what was used in the production system. So the production system basically took surname and date of birth and generated a block. So it only compared records which had the same surname at the same date of birth, and that seemed to work very well for this data set. Then we compared first name, surname, date of birth, gender, address, and postcode. And these are just the details of the machine which we've used. And I still got to find out the production system, but our version, our implementations were prototypes written in Python, which is not a very fast language. Okay, so I'll go through this very quickly as well. So this is a lot of measures which we did. We measured the scalability as a runtime, the reduction ratio, so basically, so blocking, how many record pairs were removed for the data by a blocking technique. We looked at the quality, measuring precision recall again, right? So how many true matches did we find of the true matches, and how many of the classified matches were true matches. And we measured privacy as the risk of re-identification. So we assume basically we have our masked database, and here we have a record of a Bloom filter. An attacker would have access potentially to a global database, so maybe a whole telephone book of the whole of Australia in our case. How many records in the global database can a single record be matched in our sensitive database? And based on this, we call that the probability of suspicion, and we can calculate the maximum over a database, the average, and the marketeer one, which is basically how many of the records in here have a probability of suspicion of 1. So how many can be re-identified 1 to 1? Okay, so how does it look like with regard to the results? So again, we are much slower than the production system, which is to be expected. As I said, our codes are prototype implementations, so it's 2.5, roughly 2.5 magnitude slower. If you would re-implement the privacy-preserving techniques in a different programming language, I'm sure that will come down. With regard to the blocking step, so we can see that reduction ratio is roughly the same. That basically means the privacy-preserving techniques can filter out non-matches in a similar efficient way, but the pairs completeness, so basically the recall in the blocking step is we lose a few percent here. So that basically means that compared to that fine-tuned production blocking step, our Bloom filter-based blocking step loses about 2% of true matches, which is not good, of course. Right? So that's something which you have to work on. With regard to the evaluation of matching, so again, matching is we see that we've already lost roughly 2 to 3% before in the blocking step. So now in the matching step, we're losing another few percent. So recall goes down to 0.9. So overall, we potentially going to lose in the example here 8 to 9% of the true matches, which is not very good, but that's what we're working on at the moment. Precision of the classified matches is very high. So the matches we are getting are of good quality, but we're going to lose some of the matches because of these encodings. Now, with regard to privacy, and that's of course the main aspect of our techniques compared to a non-private production system. As you can see, the red bar is the production system. You can see the disclosure risk, both the maximum, the mean, and the marketeer are very high. So there's a lot of, so the marketeer is, I don't know, 3 or something like that. So basically means a third of the linked database would still be re-identifiable as a one-to-one match with a global database. While with the privacy-preserving techniques, we are much, much better as expected, right? So the lower these bars are, the better the privacy is. In the blocking step, we're getting good results. In the matching step, we still have a problem that, again, these unique people who have a very unique name, even after all the privacy-preserving techniques have been applied, you can still identify some of them. So do a one-to-one match, and that's of course not good. Right? I'm not sure how you can ever overcome this. But otherwise, you can see with regard to the mean and the marketeer aspect, we're getting fairly good results. So the data is much more private compared to doing a non-privacy preserving approach, of course. So to summarize, so the taking privacy or using privacy preserving techniques does reduce the risk of privacy, as we hope they would. But this is one of the first evaluation on a comparison between a real production system and these prototypes, the privacy preserving prototypes. We have much higher computational costs, and we have some loss in linkage quality. So these are the two aspects which we still have to work on. The future research directions are to basically improve the computational efforts, so have more efficient filtering and communication patterns. The classification techniques at the moment in privacy-preserving record linkage most of them are very simple. Simple threshold. If the Bloom filter similarity is above a certain threshold, we say it's a match. So again, there hasn't been really lots of work in maybe using supervised privacy-preserving data mining techniques, for example. And then the other thing which we want to look into is adversary models. So these are kind of cryptographic-based approaches. So we kind of, the whole model of how do we protect our data depends on the model of the adversary. And in these techniques, we're looking at what's called the honest but curious behavior, which is the most commonly used one. And the last step is we're also working on parallelization of our techniques to basically make them faster and allow linkage of larger databases. And that's just going to end up here. Oops. Just all the references of the techniques which we compare them. Thank you.
That's fine.
Timing-wise, yeah. Okay, now we got time for questions on the details.
streaming worked as well, but it was a bit late, so I don't know.
Okay.
Who will ask
So welcome
questions.
world.
Please start with any questions.
I'll ask about the disclosure then that you said at the end that it was
Yeah.
a bit concerning. So we're told sometimes these Bloom filters are non-invertible functions so that one can't
Yeah.
get back the names and addresses
Yeah.
from what's the transform values. But what you're saying is that a lot of these transform values are actually effectively unique.
That's right. So I guess
And
yes, it's kind of you do a pattern matching between Bloom filters. You basically assume that in the where are we? So here we basically, if I'm correct, we basically assume that an attacker knows almost everything. The method being called the Bloom filters encodes a global database. And the worst case would be if the global database is the same as the actual data set. And then basically looks at which Bloom filters.
and what did you, could you remind us what you used for that? How much larger was it?
Oh no, so okay, the global database was the same as the database which we encoded. Because if you imagine if you have a larger database, then you might get let's say more like John Smith. So the disclosure risk is actually the highest if you assume the attacker has the exact same database. But yes, I mean there is because again if you have a rare name with a rare character sequence, that will end up with a certain pattern in these Bloom filters. Then you can start these.
Are there any recommendations in the privacy-preserving literature about replacing the Bloom filter by something more?
I'm not sure. So I think that's going to be talked about in the September workshop. We got 2 or 3 speakers about this. So Rainer Schnell is working on this. I've recently started to look at random projection, which actually is more computationally expensive, but overcomes these problems of the frequency distribution of the bits. And that should give us a higher privacy. But yeah, there are known weaknesses of Bloom filters, but some of the way to overcome them is to add random bits. So you add a few random bits that will modify your similarities. You might get some false positives, but if you do this in a clever way, then you can improve the privacy. Or you set a few bits to 0. So if let's say you have CY as a part in a name, which is very rare, that gives you a 1 bit. If you remove that, you still get a similarity value at the end, but you can improve privacy. So there's a lot of kind of ad hoc techniques which are being used to try to harden Bloom filters.
Any other questions, anyone else? Don't think we have any questions on the by email, or I don't know if anyone emailed you, but unfortunately, obviously, streaming happened a bit late for this talk, so people may have missed the beginning and stuff. So,
Yeah.
but it's going to be recorded, so they'll hopefully see it.
I think they also upload the slides as well normally.
I think so, yeah. So I know at least 2 people were streaming in. So
Okay, excellent.
yeah. I don't think we have any questions.
Okay, well thanks for
Thank
coming.
You, Ren. Thank you very much.